Hello, Math 201. Welcome to the final lecture in Math 201. This last section is called the U-substitution or the substitution rule, and it is an integration technique that you'll use to integrate more difficult integrals. And it's one of many if you take Calc 2 or Math 202. So let's talk about it. So remember the indefinite integral, the integral cosine x dx. Or the antiderivative cosine x dx. Remember, we know that that's sine x plus c, because the derivative of sine x is cosine x. And so the question really is given a function f of x, we know that if it's differentiable, then we can always find its derivative, right? There's always a way to calculate it, though sometimes it may be really, really hard, right? There might be some sweat and tears you need to do, but you can always do it. It's always possible, if a function is differentiable, to find its derivative. This is not the case for integrals. There are actually infinitely many functions, actually way more functions that are integrable, meaning that you can take their derivative and it will give you some quantity. So the area under their function exists, but their antiderivative is not a function we can write in terms of other functions we know. These are called transcendent functions, or they have other special kind of names, or non-elementary functions. So there's just no way to calculate this using techniques. You can approximate it really well, but there's no exact way to calculate something like this. And so the question then becomes, which functions can we integrate? And if so, how do we integrate them? And answer some of them. For our purposes, everyone that you run into in this class will be integrable. And we're gonna learn the techniques. The final technique is U-substitution on how to do it. So the first one is U-substitution, and it's based off the chain rule. This is the idea that, remember that the derivative of f of u, where u is gx, so the derivative of f composed with g of x, remember by the chain rule, is f prime of g of x times g prime of x. And I believe that actually should be, oh, okay. And so that's what they do. And so then this is the antiderivative of f with respect to u, which is going to be capital F. But anyways, what it says is that if you have a function within a function, and the derivative of that function is there, you can make a substitution. You can substitute g of x for the variable u. So you let u equal g of x, and then du, which is the derivative, right? With du means take the derivative of u, is just the derivative of g of x, which is g prime of x. And so then you substitute this part, whoops. Why am I going backwards? So g prime of x, and then we substitute this part right here, gets substituted in right there and right there. So you substitute u equal g of x, and then you substitute du equals g prime of x by taking the derivative, and that gets plugged in, right? Oh, actually, technically, there's a dx here, gx dx, because the chain rule. So that gets plugged in right there. So that's actually that whole thing. And then this gets plugged in right there. And so that's the idea, is that if you have some function that's kind of complicated in terms of x, we can make it much easier in terms of this new variable u. And as long as that variable matches that variable, now we're just integrating with f. And so in practice, how do we do this? I won't go through this. It's much easier to do through an example, but the idea is you want to find some inside function g of x. You want to make sure its derivative is sitting outside here. Then you're going to write out this table right here, and then you're going to replace them and then integrate. Okay, so let's go through an example. Let me delete this actually. It'll make it easier. Okay, so let's look at this example right here. Copy, paste. And so we want to ask ourselves, what is the inside function and what is the outside function? So it appears that, so we have 2x plus 1 cubed. And so the inside function is 2x plus 1, And the derivative of the inside function is 2. And so that is all going to work out. And so u is going to equal 2x plus 1. And then now take the derivative of both sides. And so du is going to be the derivative of this, which is 2 dx. And now we're going to plug these guys in. So this substitution gets plugged in right there. And then this substitution gets plugged in for that guy and that guy. So 2 dx. And then what are we left with? We're left with that this integral, now that we've done the u substitution, is the integral of what's left over, u cubed du. And now that's an integral we know how to do using the power rule. This is u to the 4th over 4 plus c. Now the final step is to plug this back in for u. Maybe I'll do it in a different color. So now final step is plug that in for u right there. And so this is going to be 2x plus 1 to the 4th over 4 plus c. And so that is our final answer. And if you were to take the derivative of this thing using chain rule, the 4 comes down, cancels that. You get a 3 right here. And then you have to multiply by the derivative inside, which is 2. And so we get exactly that. All right. Let's try part B. For speed's sake, I'm going to just go through it. So in this case, u is this function up here. It's going to be the thing that's inside of e because the derivative of it's sitting right here. So u is going to be 10x. And so then the derivative of u is 10 dx. We're going to plug those guys in and you get e to the u du. And so it's e to the u plus c. Now we finally plug back in u equals 10x and we get this. And so that's the basic idea of chain of u substitution, is finding what the inside function is, letting that be u, and then du is the derivative of both sides of this. So du equals 10 dx, and then you plug it back in. The issue is sometimes a function might not be readily available for chain rule. And so what happens when it's more complicated? And so let's do another one. So what about this one? So this one is off. So it's clear, hopefully, because this to the 9th power right here. Let me rewrite this. Maybe I'll put this down here. So it's clear that this x to the 5th plus 6 is the inside function because it's raised to the 9th power right here. And the derivative of this is 5x to the 4th. So this is kind of off. It's almost there, but not quite right. And so if we let u equal x to the 5th plus 6, then the derivative du is 5x to the 4th dx. This is not quite what's there, right? This is x to the 4th dx. This is x to the 4th dx, but then there's a 5 here. So how can we reconcile this? Let's divide by 5. And so you get 1/5 du equals x to the 4th dx. Now this is sitting right here for us, ready to go. And now this is what we substitute in. And so color coding this, substituting that in right there. And then now substituting this in right here, we are ready to go. So this equals the integral of 1/5. And then now it's u to the 9th du. So substituting in 1/5 du. And so now we can integrate that. That becomes u to the 10th over 10. So 1/50 u to the 10th plus c. And then finally substituting back in what u was, we get 1/50 x to the 5th plus 6. And then it will be to the 10th, yes, to the 10th power, plus c. And so that's our final answer. An alternate way we could have done this is we could have, the initial problem, this x to the 4th, we could have rewritten it as 1/5 and then 5x to the 4th. So making a 1/5 here and a 5 here to make that constant equal 1. allows so the actual du is sitting right here, because that 5x to the fourth is the derivative of that. And so that's one way. You can just kind of manipulate it so the du is already in there when it's off by a constant, and then it's just a direct substitution. You can do it like that. And so that's another way to do it. And then let's look at this guy. So this one, cosine cubed sine x, very obvious that u should be cosine of x. And then the derivative of cosine of x is negative sine x. And so we'll put the negative sign on the other side. And so it's u cubed and then -1 du. The negative sign comes out and it's u cubed du. So it's negative u to the fourth over 4 plus c. And then you plug in cosine of x. And so that one's not too bad. Let's do a little bit more difficult of one. And so this one I'm going to delete and we'll go through it. Variations on the substitution method. So this one is a little bit more intriguing. So x over square root of x plus 1 dx. So this one, you can't divide this cleanly. And so the idea is that if we let u be the bottom, then this will become in terms of u, and this will become in terms of u minus 1. And then with just a u to the square root, we can divide it cleanly. And so that's the kind of motivation. And that might seem kind of contrived, but it comes from just years of experience doing this. And so, and it's just a really simple trick that happens all the time. And so what we're going to do is we're going to let u be the bottom, x plus 1. And then du, taking the derivative of that, is just dx. So it's just a clean switch through. But then how do we deal with this x up here? Well, u is x plus 1. So that means that x is equal to u minus 1. And so these are the substitutions we're going to do. So that goes in right there. This guy will go in right here. So we get everything in terms of u. And then finally, we have to replace du and dx. And so now we get this integral. We're going to get u minus 1 over, I'm going to write it as u to the 1/2 power, and then du. And you might ask, well, why is that easier than the other thing? Well, because this is just one thing on the bottom, we can now divide cleanly into both. And so breaking up the fraction into two fractions, we get that it will be u over u to the 1/2, which is u to the 1/2, and then minus 1 over u to the 1/2, which is u to the -1/2 du. And now that is an integral we can take. And so this becomes 2/3 u to the 3/2 minus 2u to the 1/2. And then plus c. We're not quite done because we want our answer in terms of x. And so plugging in x plus 1 for u, you get 2/3 x plus 1 to the 3/2 minus 2x plus 1 to the 1/2 plus c. And that's our answer. All right. And this is the reason. A plus b over c is a over c plus b over c, but a over b plus c is not a over b plus b over c. So this is kind of the algebra for why, the algebraic motivation. So this is the algebraic motivation. Algebraic motivation on why we want to put the fraction on top. All right. Here's a general table of integrals that I'll let you look at, but it's basically the idea is that any integral that we know from before, if you put a constant in, all it does is that it puts a 1 over that constant on the outside. That's really all that this is saying. And so whenever you have a constant on the inside, the U substitution just makes it so it's 1 over constant. And we could derive that formula really easily. And so I won't really spend the time to do it. But the idea is that if you wanted to derive this, you just let u be a times x. So the derivative is a times dx. And so 1 over a times dx. And so that's how you get the 1 over a. It's nothing too crazy. The last thing I want to talk about is the substitution rule for definite integrals. And so the substitution rule for definite integrals is the exact same thing, but now we have bounds. And the only thing that changes is that you can either, there's two options. You change the bounds at the very beginning, or you plug back in what u is and then plug in the original bounds. And so I'll kind of talk through how both those go. And so let me do this one the whole way. So let me do this one fully, and I'll do it the way where you plug in the bounds at the very beginning. And so this one, we're gonna obviously, hopefully it becomes more, the more you do them, they become more obvious, but the u is gonna be the bottom function. So it's x plus 3. And so then du is just dx. So because u is x plus 3 and x goes from 0 to 2, x equals 0, that implies that u, when x is 0, u is 3. And when x is 2, that implies that u is 5. And so our new bounds are 3 to 5. And so this integral becomes the integral from 3 to 5. And then it's du becomes dx, so that's just du. And then I'm going to rewrite as u to the minus 3. So it's u to the minus 3 du. And then now this is an integral we can just do. This is a new integral that we can just work with as is. And so it's u to the minus 2 divided by negative 2, and then evaluated from 3 to 5. And so it becomes 5 to the negative 2 divided by negative 2 minus 3 to the negative 2 over negative 2. And that's the answer. So that's one way to do it. Maybe I'll do it the other way. Do I do it the other way down here? No, do I? No, I don't. The other way to do it, so let me say alternative way is like this. So instead, I can rewrite this, and I'm going to leave the x bounds. So x equals 0 to x equals 2, and then it's u to the minus 3 du. And then what does this equal? This equals u to the negative 2 to 2, x equals 0 to x equals 2. And then I plug in the x function, which is x plus 3. So it becomes x plus 3 to the negative 2, evaluated from negative 2, over negative 2, from 0 to 2. And now I can plug it in. So that equals that. And then that equals 5 to the negative 2 over negative 2 minus 3 to the negative 2 over negative 2. And you get the same answer. So those are the two ways to do it. This one, again, so u is going to be x cubed minus 7, so 3x squared. So du over 3 will be x squared dx, so that's when we're playing for that. So x is 3, that means u is 3 cubed minus 7, which is 20. When x is 2, u is 2 cubed minus 7, which is 1. So our new bounds are 1 to 20. And so it's 1 to 20. U goes on the bottom. Du over 3 goes on top. So the 1/3 comes out here, and we just get u to the minus 1 du. And so it becomes 1/3 ln of absolute value of u from 1 to 20. But then you just plug it in. And so it's 1/3 ln of 20. Nothing too crazy. Let's do this one again. And so I like to change the bounds at the beginning. It's just easier. So u is sine of x because it's sine to the 4th. Du is cosine x dx. So when x is pi over 2, you plug that into sine and you get 1. When x is 0, u is 0. So it's u, 0 to 1, u to the 4th du, which is that. Super straightforward, nothing crazy. And that's U-substitution. So that should get you through all you need for the rest of the class. All right, good luck.